There is an anomaly in the weather this April, not the kind that merits a brief mention on the evening news, but the kind that prompts atmospheric scientists to re-examine their data. As this unfolds, the eastern United States is experiencing a profound heat wave. This is not the gentle warmth of a typical spring day, but an oppressive heat pushing Washington, D.C. and Philadelphia toward 90 degrees Fahrenheit. New York City is challenging records set generations ago, while Boston, a city that only recently saw its last traces of snow, is now enveloped in air that feels more like midsummer. The first crucial detail to understand is that these cities do not typically experience such extreme heat in unison. For record temperatures to manifest simultaneously across such a vast geographic area, from the mid-Atlantic all the way to southern New England, indicates something more than a local weather pattern. This is not an anomaly, it is a signal. This widespread, synchronized heat points to a much larger, more powerful driver at play, one whose influence is being felt across a continental scale. The National Weather Service has been remarkably direct, with offices along the East Coast issuing statements that widespread records are expected to fall, a choice of words signaling a high degree of certainty. The engine behind this is a formidable ridge of high pressure, a dome of warm, sinking air parked over the eastern portion of the country. To appreciate its scale, meteorologists analyze pressure at the 500 millibar level, roughly 18,000 feet up. The anomaly over the East Coast is registering in the 97th to 99th percentile for this time of year. This means that out of every April day in recorded history, the current atmospheric structure is among the top 1 to 3%, a configuration that statistically occurs perhaps once or twice a decade. This is where the story takes a turn. The sophisticated computer systems that power modern meteorology had already identified this heat wave as exceptional. Meteorologists, using their expertise, reviewed these model outputs and adjusted their official forecasts even higher. And then the actual temperatures arrived, surpassing even those expert-adjusted forecasts. Reality outpaced both the raw computational models and the seasoned human forecasters who refined them. The atmosphere delivered more heat than our best predictions said was possible. When an event consistently outperforms every layer of prediction, it is a clear sign that something is not being fully accounted for. It suggests a component within the Earth system is responding with greater intensity than our inputs would predict. The gap between what our physics-based models say should happen and what is actually occurring is the true narrative here. A vast and powerful force, already in motion deep within the Pacific Ocean, appears to be pushing the atmosphere beyond what even our most advanced forecast models anticipated. This heat wave, it seems, is not the primary event, but rather the announcement of its arrival. What we are seeing is not the climax of some atmospheric drama, but an opening act, a preliminary signal from a system that has not yet fully revealed itself. To truly grasp the situation, we must look beyond the ground-level temperatures, because as dramatic as they are, they may not be the most significant part of what is happening. Meteorologists analyze temperature profiles through the entire column of the atmosphere, seeking a more complete picture of the forces at work. The critical question remains, what, precisely, is the atmosphere responding to? One of the most revealing measurements used to understand our atmosphere is the temperature at the 925 millibar pressure level. This layer, situated about 2,500 feet above the ground, marks the beginning of what is considered the free atmosphere. Its temperature tells a deeper story, revealing the nature of the air mass itself, not merely how the surface is reacting to sunshine. And right now, over New England, a region that in mid-April should register air mass temperatures between 5 and 10 degrees Celsius, at that height, the readings are falling between 15 and 21 degrees. This is not a small deviation. It is the distinct thermal signature of a summer air mass, one that has no business appearing in the second week of April, The warmth isn't just a surface-level event from a day of strong sun. It extends upward through the lower troposphere. This means the very air itself, the raw atmospheric material over the region, has been replaced by something that belongs in July. This distinction is thermodynamically crucial. On a typical warm day in spring, intense sunshine on dry ground can easily push surface temperatures into the 80s, even if the air mass above is only moderately warm. This creates a surface heating effect that can inflate the temperature reading. However, when the air mass itself is anomalously warm, and that heat permeates the entire atmospheric column, we are dealing with a fundamentally different phenomenon. This is an atmosphere that has been preloaded with thermal energy from a distant source, carried in on a flow pattern that is drawing warm air from places that shouldn't be producing such warmth in April. What's more, this is happening without the usual amplification from high humidity. The heat index is currently almost the same as the actual temperature across the affected region. There are no phantom degrees being added by moisture. The number you see is a pure, unvarnished thermodynamic anomaly. What makes this situation even more remarkable is what the National Weather Service has observed about model performance. The process of forecast verification, where predictions are compared to real-world outcomes, has revealed a trend that makes forecasters genuinely uncomfortable. The official forecasts, which had already been adjusted to be warmer than the raw model outputs, have still been consistently too cool. The atmosphere keeps delivering more heat than anticipated. There is a term for this: forcing mismatch. It describes a scenario where the atmosphere's response to a given set of inputs is far stronger than the known physics would suggest. Something is amplifying the system beyond the expected relationship between cause and effect. To understand this, consider a simple analogy. Imagine you set your oven to 350 degrees, but the internal thermometer reads 420. You haven't changed the input, yet the oven is producing more. In atmospheric terms, that extra output must originate from somewhere, as energy does not simply materialize from nothing. This implies there is an energy source that the models are not fully accounting for, a forcing agent whose influence is either underestimated or not yet fully integrated into our understanding of the situation. Furthermore, this high-pressure ridge is not behaving like a transient weather feature. It is not a system that has swept through and is now on its way out. The ridge has shown remarkable persistence, moving slowly and maintaining its position and intensity over the eastern United States for multiple days, as if it has settled in for a long stay. This kind of persistence is a classic characteristic of blocked patterns, which are atmospheric configurations that stall the normal west-to-east progression of weather systems, causing the same conditions to repeat day after day. Alongside the intense heat, conditions for fire have developed across parts of the region. The very same dynamics producing the warmth are also responsible for low relative humidity. When you combine anomalous heat with dry air and even a moderate wind, you create a scenario where a single spark can escalate into something much more dangerous. While not the primary story, it is a stark reminder that the consequences of this atmospheric pattern extend far beyond the discomfort of a hot afternoon. So, we are faced with an unusually deep ridge of high pressure that is outperforming model expectations, sustaining itself for days, and driven by an air mass that has no historical precedent over New England in April. This naturally leads to the same question that any atmospheric scientist would ask when looking at these numbers. What is feeding this? Something is clearly pushing the atmosphere beyond its expected limits. The answer, it seems, is not found within a weather model. It is waiting at the bottom of the Pacific Ocean. But before we journey there, we must first zoom out, because this heat wave is not occurring in isolation. It is just one component of a vast, planetary-scale atmospheric pattern that is expressing itself in 5 entirely different ways across the North American continent at the same time. When you observe all 5 of these phenomena together, the picture that emerges is far more disturbing than any single record-breaking temperature. Here we arrive at a detail that is almost never reported correctly. When you watch the news and see coverage of a heat wave in the mid-Atlantic, flooding in the Midwest, fire weather in Texas, snow in the Rockies, and severe storms across the Great Lakes, all in the same week, the events are presented as separate stories. They are covered by different anchors with different maps, as if the atmosphere had inexplicably decided to unleash 5 unrelated emergencies simultaneously. But the atmosphere does not tell separate stories. Every one of those events is a different sentence in the same paragraph. They are all expressions of a single planetary scale pattern that is currently operating at an intensity that meteorologists consider historically unusual for this time of year. The phenomenon that connects them all is called ridge-trough coupling. Think of the atmosphere as a great river of air. Under normal conditions, this river flows in a relatively smooth path, meandering gently as it moves from west to east. But under certain conditions, the very conditions we are about to explore, that river begins to develop extreme and powerful bends. A vast wave in the atmosphere is currently carving its way across the continent, creating deep southward dips called troughs that alternate with immense northward bulges, known as ridges. When these bends in the jet stream grow large and slow down, they transcend being simple weather features. They become the primary organizing force for the atmospheric behavior of an entire continent. It's a powerful illustration of how a single atmospheric event can have such varied and potent consequences. Right now, the ridge positioned over the eastern United States is one side of such a bend, responsible for driving record-breaking April heat from Washington to Boston. On the opposite side, within the trough situated over the continent's central region, the weather is a mirror image of extremes. The severe thunderstorm outbreaks currently sweeping through the Midwest and Great Lakes are a direct result of this trough. Warm, humid air from the south is being drawn northward along the trough's eastern edge, where it collides dramatically with the cooler air mass settled over the region. This is precisely the kind of atmospheric clash that fuels violent convective storms. The flooding seen in Michigan and Wisconsin is therefore not a separate, coincidental event happening alongside the heat wave. Instead, it represents the same atmospheric wave manifesting differently, as local conditions are more conducive to heavy rainfall than to extreme heat. Rivers in these areas have been hovering at or near flood stage because the persistent trough has steered repeated rounds of storms over the same locations, saturating the ground again and again. The hazardous fire weather developing in the Texas Panhandle is yet another consequence of this same ridge-trough pattern, which is pulling dry air southwestward into an area where vegetation is already under stress and humidity levels have been dropping. At the same time, the snow and freezing conditions in the Cascades and Rockies are also connected. This is the cold air being wrung out on the western flank of the trough, drawn down from Canada into the higher elevations. It is a stark contrast that produces significant late-season snowfall, even as the East Coast experiences unusual warmth, highlighting the sheer scale of this interconnected system. The physical process governing all of these phenomena is known as Rossby wave amplification. Rossby waves are enormous undulations in the jet stream, atmospheric waves so vast that they can only be properly viewed on a map of an entire hemisphere. They are not storm systems themselves, but rather the very architecture of the atmosphere on a planetary scale. And just like waves in any other medium, they are capable of amplifying. When the right conditions are met with sufficient available energy and the necessary temperature gradients, these waves grow taller. Their ridges extend further north, and their troughs plunge deeper south. The jet stream begins to look less like a gently flowing river and more like a series of sharp, dramatic switchbacks. When this amplification occurs, The extremes at each bend of the wave intensify. The heat dome grows hotter, the cold trough becomes deeper, and the boundaries between them sharpen, becoming more energetic. This leads to more severe weather, increased flooding, greater fire risk, and more anomalous warmth, all occurring simultaneously. They are all distinct expressions of the same amplified wave structure. The rarity of this situation is worth underscoring. We do not normally witness all 5 of these extreme weather categories: major heat, severe storms, flood-inducing rain, active fire weather, and significant late-season snow happening at the same time across the continent in April. While each event is unusual for the season on its own, seeing all 5 together, physically linked by a single atmospheric wave, creates a pattern that demands a deeper explanation. That explanation leads us directly to the central question of what is happening in our atmosphere. What is causing it to be this amplified in the middle of April, before the forces that typically drive such patterns have even officially begun? Historically, there is something that sets the stage for these kinds of amplified Rossby wave patterns, and it is the same phenomenon responsible for the most severe atmospheric extremes in the Northern Hemisphere. It is known as an ENSO transition. But here lies the problem and the heart of the mystery. We are technically not there yet. This makes the events we are currently observing genuinely puzzling. We must now discuss something that merits more attention, as it speaks to why this heatwave is not merely a notable weather event, but a potentially crucial atmospheric warning signal. At this moment, the official classification of the El Niño Southern Oscillation, or ENSO, is neutral. This designation means the equatorial Pacific Ocean, which acts as the great engine of global climate variability, is neither in an El Niño nor a La Niña state. The standard metric for defining ENSO status is the Oceanic Nino Index, or ONI. For an El Niño to be officially declared, this index must surpass positive 0.5 degrees Celsius and remain there for 5 consecutive, overlapping 3-month periods. By that official standard, we have not reached the threshold. The current value of the ONI is well below that mark. According to the formal accounting, El Niño has not yet arrived. The system is considered neutral, and yet it seems the atmosphere did not receive this message. The atmospheric pattern we are currently experiencing tells a very different story. We see a highly amplified ridge over the eastern United States, ranking in the 97th to 99th percentile for this time of year. Surface temperatures are running higher than every adjusted model forecast, producing record April warmth from Washington to Boston. All of this is part of the 5 simultaneous continental extremes, all linked by that amplified Rossby wave. This specific atmospheric configuration is a textbook El Niño teleconnection. It is precisely what one would expect to see if a mature El Niño were already established, driving the kind of sustained atmospheric reorganization that results from a persistently warm equatorial Pacific, injecting extra energy into the global circulation. And still, by the official metric, El Niño does not exist. What we are witnessing is a profound temporal mismatch. The atmosphere is behaving as though El Niño has already begun, while the official classification system continues to report a neutral state. Before concluding that this simply means our classification system needs to catch up, it is important to consider what this lag truly implies. The Oceanic Nino Index is, by its very design, a lagging indicator. It is calculated as a 3-month running average of sea surface temperatures in a specific part of the equatorial Pacific. This averaging process is intended to smooth out short-term variability and ensure that an El Niño is not declared every time a brief, warm anomaly appears. This conservatism is deliberate, and it holds real value for clear and reliable scientific communication. However, the price of that conservatism is that it can sometimes obscure what is actually unfolding in real time. And right now, the real-time data is telling a story that sharply diverges from the official classification. A look at the trend in the oceanic Nino index over the past 6 months reveals a very different narrative, one that suggests a significant shift is already well underway, even if it has not yet crossed the official threshold. 6 months ago, the oceanic Nino index registered negative 0.55, a figure indicative of classic La Niña conditions across the cold equatorial Pacific. In the time since, a profound shift has taken place. The index has climbed to negative 0.16, a warming trajectory of nearly 0.4 of a degree in just half a year. With this consistent upward momentum, the system is on a course to cross the El Niño threshold not in some distant future, but potentially within weeks. Yet, a crucial question arises. Why are we already witnessing weather patterns that resemble El Niño before it has been officially declared? The answer lies in the continuous dialogue between the ocean and the atmosphere, a conversation that occurs more rapidly than any of our official classifications. Warm water in key locations fundamentally alters atmospheric convection, which in turn redirects the jet stream. These changes are manifesting as the exact atmospheric patterns we see across North America today. The atmosphere is not responding to a statistical index. It is reacting to the physical state of the ocean, which is already significantly further along than the official numbers suggest. However, the warming we can measure at the ocean's surface, the very signal the ONI is slowly starting to capture, reveals only a fragment of the larger picture. The true story is not unfolding at the sunlit surface of the Pacific. It is happening hundreds of meters below, in a layer of water that no satellite can directly observe. Down in these depths, an extraordinary amount of thermal energy has been steadily accumulating. This raises a profound point. When this hidden heat eventually rises, it carries the potential to change everything. And now we are watching it begin its journey. The explanation for the atmosphere's recent behavior was never in the sky. It was always waiting in the deep ocean. What lies beneath the surface of the Pacific is something that warrants our careful attention. To truly grasp the forces driving recent events, we must look beneath the waves. This is perhaps the most important concept to hold in mind. Everything we have observed so far, the record April heat, the amplified Rossby wave patterns, and the atmosphere behaving in ways that defy model expectations, is merely a surface-level expression of a process occurring in the dark, cold waters hundreds of meters below the equatorial Pacific. If we want to understand why this recent heat wave is more than just a weather event and is instead a critical warning signal, we must first understand the incredible phenomenon that is moving through the ocean right now. Data from the Copernicus Marine Service has provided numbers that give oceanographers pause. In specific regions of the subsurface equatorial Pacific, at depths between 100 and 300 meters, temperature anomalies are reaching approximately 5 degrees Celsius above average. To place this figure in context, a 2-degree anomaly in this region is powerful enough to force a major reorganization of global atmospheric circulation. A 3-degree anomaly is what typically produces a strong El Niño event. A 5-degree anomaly in the subsurface water column represents a thermal load so immense that, when it surfaces, it could rewrite the atmospheric rulebook for the entire planet. And this vast reservoir of heat is not stationary, it is migrating. This eastward movement is being carried by a powerful oceanic mechanism known as a downwelling Kelvin wave. These are not the familiar waves that break on a beach. Instead, they are massive, subsurface pressure waves that travel from west to east along the equator, carrying with them a deepening of the warm water layer. As a downwelling Kelvin wave passes, it pushes the thermocline, the boundary separating warm surface water from cold deep water, further down. This process effectively buries the cold water, allowing the upper ocean to heat up. When this occurs on a sufficient scale, it primes the eastern Pacific for a dramatic surge in surface temperatures, which can then directly interact with the atmosphere above. The engine driving these Kelvin waves is a series of westerly wind bursts in the western Pacific. These are brief but potent reversals of the typical trade winds, and each one generates a subsurface pressure pulse that becomes a new wave. These bursts have been happening repeatedly over the last several months, with each one sending another pulse of thermal energy eastward across the ocean. You can visualize this as the ocean receiving repeated, methodical pushes of energy, rather than a single, large event. It is a sustained series of impulses, each one contributing to the eastward migration of that enormous pool of warm subsurface water. The system is being loaded, and the heat, 5 degrees above normal, is still traveling, still building, and not yet at the surface. The connection between this subsurface activity and the April heatwave is direct and tangible. Warmer ocean temperatures, even when they are still deep, alter the patterns of atmospheric convection in the western Pacific and the tropics. This change affects both the Madden-Julian oscillation and the Walker circulation, which in turn modify the position and energy of the subtropical jet stream. These jet stream alterations then propagate downstream, moving eastward to influence the circulation patterns over North America. The enhanced ridge of high pressure, the amplified Rossby waves, and an atmosphere outperforming all models are the downstream fingerprints of an ocean that has been building toward this moment for months. The subsurface anomaly is the engine, and we are just now beginning to see its effects on the surface. The intense heat of April can be seen as the exhaust from a planetary engine that has yet to reach its full power. This is the 6th part of our exploration. To understand a critical problem that often hides in plain sight during discussions of El Nino, it helps to begin with a thought experiment. The issue is not that the science is incorrect, but that our methods for classifying vast natural phenomena can lag behind the reality they are meant to describe. Imagine a physician trying to diagnose a patient's fever. They have 2 instruments. The first is a thermometer, providing a real-time reading, a direct measurement of the patient's condition at this very moment. The second is a rolling 3-month average of their temperature, smoothed to filter out daily fluctuations and reveal their broader thermal history. Both tools are scientifically valid, but they serve different purposes. One tells you what is happening now, the other tells you what has been happening over a longer period. The oceanic Nino index, or ONI, operates much more like that 3-month average than the instantaneous thermometer. It is intentionally designed to smooth out brief variations in sea surface temperatures within the crucial Nino 3.4 region of the equatorial Pacific. This smoothing is a feature, not a flaw. It allows scientists to avoid false alarms, ensuring that a classification of El Nino or La Niña reflects a sustained state rather than a temporary spike. But this stability comes with an inherent trade-off, a delay. The ONI does not lead the climate system, it follows it. By the time the index officially crosses the threshold for an El Nino, a sustained anomaly of plus 0.5 degrees Celsius or higher over several overlapping 3-month periods, the ocean itself has typically been warming for weeks or even months. In a very real sense, the official classification is simply catching up to a process that was already well underway. This brings us to where we are right now. Just 6 months ago, the ONI registered approximately negative 0.55 degrees. This was not merely neutral, it was firmly in La Niña territory. At that time, the Pacific was defined by cooler than average surface waters in its central equatorial belt, and the atmospheric patterns associated with La Niña were dominant. Trade winds blew stronger, pulling warm water farther to the west. The entire system was operating in its cold phase. But then, a shift began. The ONI moved from negative 0.55 to roughly negative 0.39, then to negative 0.24, and most recently to negative 0.16. Each update, representing a new 3-month rolling window, has marked another step upward along a clear and consistent warming trajectory. On paper, the official classification for this state is still neutral, but the direction of travel is unmistakable. If one were to extrapolate this trend forward, the index is on a path to cross zero, the point where the anomaly turns positive in the very near future. From that point, reaching the plus 0.5 degree threshold required for an official El Niño declaration becomes less a question of times, if times, and more a question of timing. It could be a matter of weeks, or perhaps a couple of months, depending on how rapidly the warming continues. However, focusing solely on that official threshold risks missing the deeper story. While the ONI still hovers below the line, the leading indicators, the real-time signals of where the system is headed, are already far ahead. The most significant of these signals lies hidden beneath the surface of the Pacific Ocean. In some regions, subsurface temperature anomalies are running as high as 5 degrees Celsius above average. This is not a subtle deviation. It is a massive reservoir of heat stored deep below the surface, now moving eastward along the equator in the form of downwelling Kelvin waves. These waves are not theoretical models. They are measurable, trackable pulses of exceptionally warm water that propagate across the vast expanse of the Pacific. As they travel, they deepen the thermocline, the boundary between the warmer surface waters and the colder deep ocean, and push that stored heat toward the surface in the central and eastern basin. When these waves finally arrive and begin to surface, they often mark the critical transition from a subsurface, preloaded state to a fully realized El Niño at the surface. Right now, that very process is underway. The ONI, by its design, cannot capture this subsurface heat directly. Its mandate is to measure only sea surface temperatures, and even then, only as a smoothed average over time. So, while the ocean depths are already reorganizing for a major shift, the official index is still factoring in older, cooler data from previous months. The result is a single number that understates the true speed and magnitude of the current transition. If you change your perspective from 3-month averages to weekly data, the picture sharpens dramatically. Recent sea surface temperature readings in the Nino 3.4 region are already running warmer than the ONI would suggest, precisely because the most recent weeks have seen an acceleration in warming. The averaging process dilutes that urgent signal, blending it with earlier, cooler weeks that no longer reflect the ocean's present state. It is the difference between looking at a slow-moving average and watching a dynamic system in motion. And when you observe this system in motion, it does not look neutral at all. It looks like a system actively and rapidly transitioning toward El Niño conditions. History offers a useful, if slightly unsettling, comparison. Before the 1997 to 1998 El Niño, which remains one of the most powerful in the modern record, the Pacific displayed a similar pattern. A significant buildup of subsurface heat began migrating eastward for months before the surface temperatures crossed the official thresholds. Scientists who were tracking these deeper ocean signals saw the potential for a major event developing well in advance. However, those relying primarily on surface indices like the ONI saw a system that still appeared neutral or only weakly positive. When the atmosphere finally responded, it did so with a speed and intensity that caught many off guard. A comparable, though not identical, pattern also preceded the 2015 to 2016 El Niño. Once again, subsurface anomalies provided an early warning. Once again, the official classification lagged behind the underlying physical reality. The lesson from these events is not that the ONI is flawed, but that it is incomplete as a real-time diagnostic tool. It tells you what the system has been doing with great reliability, but it does not fully capture what the system is about to do. And right now, The gap between those two perspectives is widening. The trend within the ONI itself is already signaling rapid change. A shift of roughly 0.4 degrees Celsius over the course of 6 months is not trivial. It indicates a system in a state of profound transition, moving decisively away from La Niña conditions and towards something much warmer. The question is no longer about the direction, but about the destination. The subsurface temperature data, the weekly surface trends, and most critically, the atmospheric behavior we are witnessing in real time all point to the same conclusion. This transition is much further along than the official index alone might suggest. This is where the atmosphere's role becomes impossible to overlook. It does not wait for an abstract number to cross a designated threshold before it begins to shift. Instead, the atmosphere reacts directly to the physical distribution of heat within the ocean, responding to thermal gradients, anomalies, and the delicate, changing balance of energy between the sea and the air. What we are currently observing across the United States, the record-shattering April heat, an unusually persistent ridge of high pressure, and simultaneous extremes in different regions is entirely consistent with an atmosphere already reacting to a warming Pacific. It is not yet responding to a fully formed El Nino, but rather to its precursor state, the critical loading phase. It is as if the entire system has begun to reorganize itself in anticipation of what is coming, rather than waiting for an official declaration. This context is precisely why the April heatwave carries significance far beyond its immediate impact. A stretch of temperatures in the 80s and 90s during April, while certainly uncommon, is not without precedent. However, when it unfolds in lockstep with a Pacific Ocean that is rapidly warming beneath the surface, and when it aligns with atmospheric patterns that mirror those of a mature El Niño, it transforms into something more. It becomes a piece of evidence, a signal that the atmosphere is responding to conditions that our official classifications have yet to fully recognize. It suggests the system is, in a sense, running ahead of schedule. And this, in turn, raises a crucial question. If the atmosphere is already generating this level of response while the oceanic Nino index remains below the El Nino threshold, what can we expect when that line is finally crossed? What happens when the vast reservoir of subsurface heat fully breaches the surface, when the feedback loops between the ocean and atmosphere intensify and complete their coupling? This is not a question that comes with a simple or precise answer. Yet, it becomes more urgent the more we appreciate the inherent limitations of the very tools we use to define our present state. The oceanic Nino index will, eventually, confirm what is occurring. It will cross into positive territory and, if the current trajectory holds, it will meet the criteria for an El Nino event. When that happens, it will provide a clear, official label for the state of the system. But by then, the system itself may have already been operating in that mode for a considerable time. This means that anyone relying exclusively on that label to understand what is happening is always looking slightly in the rearview mirror. The true story is unfolding now, written in the leading indicators in the subsurface heat, the swift surface warming, and in an atmosphere that is already behaving as if the transition is well underway. And that brings us directly to the next piece of this intricate puzzle. If the subsurface reveals where the system is headed, and the atmosphere shows how it is already responding, then the ocean surface itself shows us what happens when that hidden energy begins to break through into full view. This brings us to a phenomenon unfolding along the California coast, a development that could be described as a shock to the system. There is a stretch of ocean there right now that does not look or behave like it should in April. If you were to see only a map of the data, a single snapshot without context, you might be forgiven for assuming an error in the measurement itself. The latest sea surface temperature anomaly maps for the northeastern Pacific are not just showing unusual warmth. They are displaying record-breaking conditions that force a recalibration of what we thought was possible this early in the year. According to the high-resolution global data from NOAA's Coral Reef Watch, the waters off the California coast are currently at their warmest ever recorded for the month of April. This is not the warmest in a few years, or the warmest since the last major marine heatwave. It is the warmest in the entire observational record for that region during this specific month. And this is no small, isolated patch hugging a particular section of the shore. The anomaly extends southward along Baja California and then stretches far out into the central Pacific. There, it connects seamlessly with a much broader band of exceptionally warm water that runs clear across the ocean basin, all the way toward the Marshall Islands in the western Pacific. What we are witnessing is not merely a hotspot, it is a coherent system. It is a continuous, basin-scale structure of elevated ocean temperatures, which happens to be expressing some of its most extreme values right along the Pacific coast of North America. It is as if the ocean itself is drawing a line from one side of the Pacific to the other, signaling that this is not regional variability, but a coordinated, fundamental shift. To truly grasp how extreme this shift is, one must understand how marine heat waves are classified. The system used by NOAA and other research institutions sorts these events into 5 levels. Category 1 signifies moderate conditions, warm, but within a range that ecosystems can sometimes withstand. Categories 2 and 3 represent escalating severity. By Category 4, conditions are considered extreme, already pushing marine life beyond what it is adapted to handle. And then there is Category 5. This final category is not just very extreme. It describes conditions that surpass the historical range for a given location and time of year by such a wide margin that they fall outside what the climatological record would consider normal variability. In other words, you are no longer dealing with an unusually warm ocean. You are observing a state that, based on all past data, simply should not be occurring. Right now, off the coast of Baja California, that is exactly where the system is operating, Category 5. This means the sea surface temperatures there are not just above average, they are above the previous extremes, surpassing the highest values ever recorded for April in that region. It is the kind of signal that compels scientists to double-check their instruments, to cross-reference satellite readings with buoy data, and to confirm that what they are seeing is real. And it is real. This is not a measurement artifact. The phenomenon is being observed across multiple, independent datasets, from satellites in orbit to buoys floating in the water, all telling the exact same story. The instruments are not mistaken. They are simply bearing witness to an unsettling new reality taking shape in the Pacific. The waters of the northeastern Pacific are exhibiting an extraordinary warmth, a phenomenon that aligns perfectly with a much larger pattern we have been observing across the entire basin. To truly grasp its significance, however, we must look not at the surface but to the processes unfolding far beneath it. This surface anomaly is not a spontaneous event. It is the culmination of months of change. For some time, the Pacific Ocean has been steadily accumulating a vast reservoir of heat below the surface, manifesting as the subsurface anomalies areas 5 degrees Celsius above average that we have previously discussed. This immense pocket of thermal energy has been migrating eastward along the equator, carried by downwelling Kelvin waves on a slow, deliberate journey toward the eastern edge of the ocean. When this tremendous volume of warm water finally reaches the coast of the Americas, a critical transition occurs. The ocean effectively runs out of eastward space, and the energy that was stored deep below the surface has nowhere to go but up. Under normal circumstances, the coastlines of California and Baja California are dominated by a process known as upwelling. Here, coastal winds push surface waters offshore, allowing colder, nutrient-rich water from the depths to rise and take its place. This natural cycle is the very foundation of the region's vibrant marine ecosystems, explaining why these coastal waters are typically cool, even when the open ocean is warm. But this entire process rests on a single vital assumption, that the water being drawn up from below is, in fact, cold. Today, that fundamental assumption is being challenged. The deep water is no longer cold, it is anomalously warm. As upwelling continues, it is no longer bringing cool, life-sustaining water to the surface. Instead, it is pulling from the vast subsurface heat reservoir that has been building for months. Consequently, the upwelling process, which should cool the surface, is now reinforcing the warmth. It is akin to turning on a tap that once provided cold water, only to discover the entire plumbing system behind the wall has been heated. No matter how long you let it run, the water will not cool down because the source itself has been fundamentally altered. This reveals why the marine heat wave off the coast of Baja is not an isolated incident. It is simply the next chapter of the same story, the visible release of a thermal event that has been developing silently, now breaking through to the surface where it can interact directly with the atmosphere above. And it is this interaction with the atmosphere that makes the situation profoundly relevant to weather patterns over land. A warm ocean surface is not a passive feature. It is an active participant in our climate system. It constantly exchanges energy with the air, transferring both heat and moisture, which in turn alters atmospheric pressure and influences the formation and stability of ridges and troughs. A Category 5 marine heat wave is more than just a number on a chart. It represents a massive repository of thermal energy positioned at the critical boundary between the ocean and the air, feeding directly into the atmospheric engine. The sheer scale of this is difficult to overstate. This is not a small, localized feature. It extends for hundreds of miles along the coast and is connected to a basin-wide anomaly stretching thousands of miles across the Pacific. The immense energy involved is now situated adjacent to a continent already witnessing an atmospheric pattern pushed to the extreme edge of its historical behavior. A persistent ridge over the eastern United States, sitting in the 97th to 99th percentile, is already pulling in and reorganizing heat. The jet stream is highly amplified, and the system as a whole is generating multiple, simultaneous weather extremes. Into this already volatile setup, we now introduce a coastal ocean that is pumping additional heat and moisture into the atmosphere. This is where proximity becomes critically important. The closer this oceanic heat source is to land, the more directly and powerfully it can shape the atmospheric processes that dictate our weather. This creates a dangerous feedback loop. Warmer ocean surfaces lead to increased evaporation, which injects more moisture into the air. This moisture then enhances the release of latent heat within storms and other circulation systems, adding yet another layer of energy to dynamics already being driven by the larger pattern. It is a compounding effect, where a subsurface reservoir feeds the surface feeds the atmosphere, and the atmosphere responds in ways that amplify the entire circulation. All of this is unfolding on top of a global ocean baseline that is already at a record high. This is not a simple, linear system of cause and effect. It is a complex network of interactions, with each component amplifying the others. That is why the anomaly off the California coast is so significant in the context of the April heatwave. It is not just a regional point of interest. It is a clear, measurable confirmation that the Pacific has begun to release its stored heat at the surface, consistent with the development of a much larger event. It signals that the system is no longer just loading energy, it has started to discharge it. When we examine the structure of this release, noting how it connects the California coast all the way to the western Pacific, we begin to see patterns that echo the past. There have been moments in the historical record when similar basin-wide warming preceded major El Nino events, moments when the Pacific acted as a single, unified system. However, this is where the current situation diverges from its historical analogues. Those past events did not begin from a baseline as intensely warm as the one we see today. They did not start with a global ocean that had already shattered records for its highest average temperature. They did not combine a Category 5 marine heatwave off the California coast in April with a subsurface anomaly of this scale, all while the atmosphere was already responding ahead of schedule. The historical parallels are useful, offering a glimpse of what the system is capable of, but they are ultimately incomplete. They cannot fully capture what might happen when those same processes operate upon a higher energy baseline, and it is in that unknown territory that a sense of profound unease begins to settle. When we look to the past for a map of the present, we find the comparison is not exact. While the individual elements seem recognizable, their arrangement is entirely new, suggesting that future outcomes may not align with the patterns we have come to expect. What we are witnessing along the California coast is more than just an anomaly. It is a profound signal. It indicates that the ocean has entered a state capable of generating conditions that lie outside the bounds of our historical records for this season. Because the ocean is the primary engine driving our atmosphere, this shift forces us to reinterpret everything that follows. The April heat wave is no longer an isolated incident, but a chapter in a larger, unfolding story. The atmospheric ridge, the temperature extremes, and all associated anomalies are now interacting with a Pacific Ocean that is revealing its immense power, and its message is anything but subtle. It tells of a system holding far more energy than it should at this stage, an energy it is already releasing in multiple, powerful ways. This suggests the processes we are observing are not concluding, they are only just beginning. This situation recalls a recent and disruptive event in the ocean's memory. Between 2013 and 2016, a vast expanse of unusually warm water materialized in the northeastern Pacific. Scientists gave it the name, the blob, a label whose whimsical sound stands in stark contrast to the profound ecological and economic disruption it caused. This marine heat wave fundamentally altered the California current, the system of cold, upwelling water that has defined the northeastern Pacific for as long as we have measured it. It dissolved the cold water barrier that typically contains tropical marine life, allowing species from hundreds of miles south to appear off the coasts of Oregon and Washington. Its influence extended beyond the ocean, contributing to the most severe drought in California's recorded history and triggering the collapse of the Pacific sardine fishery. The blob also fueled immense toxic algal blooms stretching from California to Alaska, forcing shellfish closures across thousands of miles of coastline. At the time, it pushed sea surface temperature anomalies to levels never before seen in the modern observational record, setting an alarming new benchmark for what was possible. The temperature anomalies being measured off the California coast today are, in terms of sheer magnitude, comparable to those produced by the blob at its most intense. Yet, a critical distinction separates that event from the present situation, a difference that makes our current circumstances potentially far more consequential. The blob emerged as the equatorial Pacific was shifting toward what would become the major 2015 to 2016 El Nino. However, the blob itself was not part of that El Nino. It was a distinct anomaly in the Northeast Pacific that happened to coincide with, and compound, the equatorial warming. The two signals ran in parallel, but they possessed different origins and were driven by separate primary mechanisms. What is unfolding now appears structurally different. The current marine heat wave in the Northeast Pacific is not merely running alongside an equatorial anomaly, it seems to be deeply connected to it, the basin-wide warming pattern that NOAA is tracking. A continuous stretch of heat from the Marshall Islands in the west to the coast of California in the east points toward a single, coherent thermal event. This implies a level of systemic integration that is not well represented in our climate models. We may be witnessing not the blob plus a developing El Nino, but rather a single, basin-scale thermal event with very little historical precedent. This distinction is profoundly important because of a principle known as nonlinear amplification. It is a reminder that, in complex systems like our planet's climate, 1 plus 1 does not always equal 2. When two separate, extreme events occur in the same time and place, they can generate impacts that are far greater than simply adding their individual effects together. The atmosphere does not process two distinct forcing signals independently and then sum the results. Instead, it responds to their combined presence, and this combination can unlock feedback loops and interactions that neither event could have produced on its own. A massive marine heat wave in the northeast Pacific, coinciding with a developing equatorial El Nino, is not, in terms of its atmospheric influence, just the sum of its parts. It is a compound event, whose total effect on atmospheric circulation could dramatically exceed what either component would create in isolation. The challenge is that we lack a robust set of historical examples of such a compound event at this scale, leaving us without a clear guide for what to expect. The uncertainty we face is therefore genuine and significant. What we can state with confidence is that the Pacific Ocean, from its surface down to depths of hundreds of meters, currently holds an accumulation of thermal energy that is historically unusual, even for a period preceding an official El Nino. The anomalies beneath the surface are already larger than those that preceded major past events. At the surface, the warming is so intense that it has reached Category 5 marine heatwave intensity in some areas. The sheer coherence of this warming pattern across the entire basin suggests a system that is more interconnected and energetically charged than a typical pre-El Nino state. And the planet's climate system is reacting not to a hypothetical future, but to the tangible reality of the ocean's current state. It is already responding to this precursor condition. If this preliminary state is already capable of producing record-breaking April heat waves ranking in the 97th to 99th percentile of atmospheric intensity, it raises a deeply consequential question. What might the fully developed event look like? There is no comfortable answer. To begin to form one, we must first understand the precise mechanism that transforms ocean heat into atmospheric chaos. The connection between a warm Pacific and a heat wave in Boston is not immediately obvious. But once that bridge is understood, the potential scale of what is coming becomes much harder to dismiss. To understand this connection, we must look to the jet stream, a crucial component of Earth's heat regulation engine. Imagine it as a vast river of air flowing from west to east around the northern hemisphere at an altitude of roughly 30,000 feet, carrying our weather systems along with it. In its normal state, this river meanders gently, with modest deviations allowing for an efficient flow of air and energy around the globe at a reasonable pace. Now, picture what happens when you warm the ocean beneath its southern flank. This adds a tremendous amount of energy to the tropical and subtropical atmosphere, which in turn changes the temperature contrast between the tropics and the polar regions. When this temperature difference shrinks, either because the tropics warm faster than the poles, or because the poles themselves are warming significantly, as they have been, the jet stream loses its strength. And a weakened jet stream is one that begins to meander far more dramatically. As the jet stream's path distorts, its gentle curves warp into dramatic bends. The northern ridges push farther toward the pole, while its southern troughs plunge deeper toward the equator. In this state, the atmospheric river resembles less of a streamlined highway and more of a powerful force carving through solid rock. This phenomenon is known as Rossby wave amplification, and it is the precise atmospheric mechanism that can transform a warm Pacific Ocean into a catastrophe for an entire continent. The Rossby waves currently unfolding over North America are anything but subtle. Over the eastern United States, the ridge and northward bulge in the jet stream is registering in the 97th to 99th percentile for height anomaly at this time of year, a deviation that is statistically without precedent in the April historical record. Its counterpart is the deep trough over the center of the continent, a southward plunge driving severe weather and flooding. The amplitude of this wave, measured as the distance from the ridge's peak to the trough's basin, is so extreme that it is capable of producing all 5 categories of simultaneous extreme weather catalogued by scientists. This is not a minor atmospheric fluctuation. It is a powerful demonstration of a direct physical connection between the thermal state of the Pacific and the weather patterns we experience on land. The process linking the ocean's warmth to these amplified Rossby waves originates with tropical convection. When the surface temperature in key areas of the tropical Pacific exceeds approximately 28 degrees Celsius, it crosses a critical threshold for deep convection, causing thunderstorm activity to intensify and organize into vast systems. These storms then heat the upper troposphere through a process called convective heating, which occurs as moisture condenses at high altitudes and releases latent heat energy. This warming in the upper atmosphere generates pressure anomalies that then propagate poleward, traveling through the atmosphere as Rossby waves. In essence, the energy from tropical thunderstorms, fueled by a warm Pacific, journeys north and northwest until it reaches the jet stream, where it fundamentally reshapes the existing wave pattern. The relationship is direct. A warmer Pacific leads to more intense convection, which in turn creates stronger Rossby wave forcing and a more amplified jet stream. This is not a theoretical model, but a well-documented and understood physical pathway that connects ocean temperatures to weather extremes thousands of miles away. And when we examine the current state of that pathway, we find it is far more energized than is typical for April. The reason for this is that the ocean temperatures driving the tropical convection are already at levels that would normally correspond to a fully developed El Nino, not a neutral or transitional phase. Several factors are contributing to this powerful atmospheric response. The significant subsurface warming we have been tracking, the surface anomalies that are approaching the intensity of a Category 5 marine heatwave, and the sheer basin-wide coherence of this thermal anomaly are all combining. Together, they are generating a Rossby wave forcing so strong that the atmosphere is reacting with the full amplification we see in the current pattern. This is all happening before the El Nino system has even officially arrived. The wave is already operating at maximum amplitude. The ridge is already touching the 99th percentile, and the heat is already shattering April records. This raises a profound question. What will happen to the wave's amplitude when the vast reservoir of subsurface heat finally finishes surfacing, and the full equatorial Pacific warming begins to generate the kind of sustained convective forcing that only a mature super El Nino can produce? While we cannot know for certain, the trajectory of the physics points in a clear direction, as the atmosphere seems to be showing us the answer before the question has even been fully asked. It is worth briefly touching upon a related scientific debate concerning whether the increasing frequency and amplitude of these Rossby wave events in recent decades can be directly attributed to climate change, specifically to Arctic amplification. This phenomenon, where the Arctic is warming roughly 4 times faster than the global average, reduces the temperature contrast that helps keep the jet stream strong and stable. However, its precise impact remains an area of active research and genuine scientific disagreement. While some studies indicate a clear statistical link between Arctic warming and a more meandering jet stream, others find the signal to be less distinct or possibly obscured by natural variability. The honest assessment is that the science on this particular connection is not yet settled. But what is not debated are the fundamental physics of the event unfolding right now. The atmosphere over North America is currently exhibiting a wave pattern of extraordinary amplitude. The Pacific Ocean below it is anomalously warm, both at the surface and to depths and extents that dwarf typical April baselines. The energy source is real, The atmospheric response is real, and the combined implications are what we must consider when we ask what comes next. There is a concept in atmospheric science that, while rarely discussed in mainstream weather coverage, is perhaps the single most important idea for understanding why this April heatwave is more significant than it might appear. That concept is preconditioning. The term means exactly what it implies. A system is being set up, primed and loaded with both energy and a structural bias long before the main event arrives. Consider the difference between trying to topple an untouched wall and trying to topple one whose foundation has already been undermined. The same amount of force will produce dramatically different outcomes depending on the initial state of the target. The wall that has been preconditioned, its structural integrity already compromised, will fall with far less effort than the one that began from a neutral baseline. The current state of the atmosphere over North America and the Pacific Ocean beneath it is precisely such a preconditioned system. This preconditioning has been underway for months, and it can be described in specific physical terms. The vast pool of subsurface Pacific water, with temperatures 5 degrees above average and migrating eastward, does not simply sit inertly in the deep ocean. It is not a passive observer waiting for its moment to surface. Even while it remains deep, its presence actively alters the sea surface temperature pattern through heat exchange. It changes the depth of the thermocline and, critically, suppresses the upwelling of cold water that would otherwise cool the surface from below. This means that for months, the surface of the Pacific has been warming more consistently and intensely than it would have without this subsurface loading. In effect, the entire ocean atmosphere system has been primed, setting the stage for a more extreme and rapid response once the main event truly begins. Even a seemingly modest rise in surface temperatures has been enough to disrupt the vast machinery of the atmosphere above it. This warming has shifted patterns of convection, altered the Walker circulation that links the tropical Pacific to the rest of the globe, and reshaped the powerful subtropical jet stream. For weeks and months, this modified jet stream has carried its new structure eastward, influencing the weather over North America. This process suggests the atmosphere has a kind of memory, where each day's circulation pattern serves as another layer of conditioning for what is to come. The result is that the enormous ridge of high pressure, now registering in the 99th percentile for April, was not a sudden event. It was the culmination of a slow, persistent build-up, driven by an ocean that had been storing and releasing this energy for months. This gradual preconditioning helps explain why many predictive models failed to anticipate the true intensity of the resulting heat wave. The models could identify the basic ingredients for warmth, but they struggled to fully grasp the significance of the background state. They were not designed to account for how months of subtle forcing from the Pacific had already primed the atmosphere, making it far easier to construct such an extreme ridge. It raises a critical question about our predictive capabilities. If the very foundation of the atmosphere is shifting, how can our models keep pace? In recent years, we have seen a growing number of atmospheric extremes that arrive well ahead of their typical seasonal schedule. This has sparked a legitimate scientific debate about whether these events represent a true, underlying trend, a signal, or are simply random statistical fluctuations, or noise. However, the current event is so pronounced that it challenges the notion of being mere noise. A ridge of high pressure reaching the 99th percentile for April is not a minor deviation. It is a profoundly extreme occurrence. Its sheer intensity, when compared against the historical baseline for this time of year, points toward a fundamental change in the background state of the atmosphere, something beyond the scope of natural variability alone. What this suggests is that the threshold required to trigger such an extreme event in April has been lowered. The climate system appears to have become more sensitive, now needing a smaller push to generate a much larger response. This is the very definition of preconditioning on an atmospheric scale. The profound implication is that our long-held assumptions about the timing of seasons may no longer be reliable. The idea that July's extreme weather should stay in July is being actively challenged, suggesting the familiar rhythm of the seasons is beginning to falter. This brings us to the critical concept of threshold crossings. The Earth's climate is one of the most complex systems known, and such systems often exhibit a particular behavior. They can respond in a predictable, linear fashion for long periods, only to change abruptly and dramatically when a hidden boundary is crossed. While we cannot map out every one of these thresholds with certainty, we know they are an inherent feature of the climate. When a system is steadily preconditioned over months, as the atmosphere has been, it is pushed ever closer to one of these tipping points. Once near that edge, the trigger required to initiate a crossing can be astonishingly small. In this state, a relatively modest, immediate force applied on top of the accumulated preconditioning can unleash a disproportionately massive response. The atmosphere we are witnessing now is not simply reacting to the day's weather conditions in a proportional way. Instead, it is responding to the sum total of months of background loading combined with the immediate trigger. This cumulative effect is what has produced a heat wave so powerful that it has exceeded the projections of every model, even after they were adjusted. This leads to a deeply unsettling question. If this is the atmospheric response from preconditioning alone, what might happen when the primary drivers of the season fully manifest? To find more context for this question, we must turn our attention away from North America for a moment. While the eastern United States endured this record heat, the western Pacific was quietly offering another, equally powerful piece of evidence that the ocean was operating far outside its normal seasonal boundaries. That evidence arrived in the form of a monstrous storm, a typhoon that reached Category 5 intensity at a time of year when such a thing should be nearly impossible. In April of 2026, Super Typhoon Sinlaku churned through the western Pacific, its winds achieving the highest rating on the Saffir-Simpson scale. A Category 5 storm in April is a profound anomaly. While the western Pacific basin can produce tropical cyclones year-round, storms of this magnitude are exceptionally rare this early in the season. The reason for this rarity is simple. The necessary fuel is usually absent. Tropical cyclones require vast amounts of thermal energy, needing ocean surface temperatures of at least 28 degrees Celsius to power their convection and fight off the dry air and wind shear that typically weaken early season storms. Yet, Sinlaku not only formed but rapidly intensified over a wide expanse of the western Pacific where waters were 28 to 29 degrees Celsius. These are temperatures that belong to the peak of the season in July or August, not April. The ocean heat content, which measures the total energy available down through the water column, was also equivalent to peak season levels. In a very real sense, the storm was oblivious to the calendar month. The ocean provided no indication that it was only April. This event connects directly back to our central narrative. Super Typhoon Sinlaku is not a separate, unrelated phenomenon. It is a crucial data point from the other side of the world confirming the same underlying signal. In April 2026, the Pacific Ocean was warm enough to simultaneously generate a peak season typhoon in its western basin, a record-breaking marine heatwave in the northeast, and Category 5 marine heatwave conditions off the coast of Baja California. This demonstrates that the thermal anomaly is not a localized or regional issue. It is a systemic condition, expressing itself across the entire Pacific, and in each location, it is producing extreme events that are months ahead of their historical schedule. Both Sinlaku and the North American heatwave are telling the same story from different perspectives. The ocean is already operating at a heightened state, and the atmosphere is responding with extremes that are profoundly out of season. But there is one final number that puts all of this into a stark, global context. This figure is not from a model or a future projection. It is a direct measurement of our world. In March of 2026, the global ocean surface temperature set a new record. This was not merely a record for the month of March, nor was it just a seasonal anomaly. It was the highest average sea surface temperature ever recorded for any month in the entire history of observation. This single fact suggests the entire baseline has shifted. In March of 2026, the global ocean reached a temperature warmer than any previously recorded in modern history, when averaged across the entire planet. At first, this might seem like just one more signal in a long series of warming trends. Yet, it represents something far more significant than a single data point. This event fundamentally alters the very context in which all weather, both present and future, will materialize. The crucial difference in this moment is not merely the anomaly, the deviation from an established average, but the absolute baseline itself. It is as if the very floor of our planet's climate system has been permanently raised. This distinction is often missed, as discussions about weather tend to focus on anomalies, how far a particular event strays from the norm. But anomalies only reveal part of the picture. They show how unusual an event is compared to a past average, not its absolute intensity. And as the baseline shifts upward, the very meaning of every anomaly is transformed along with it. To visualize this concept, we can imagine a vast swimming pool. The level of the water in this pool represents the baseline temperature of the global ocean. The waves that ripple across its surface are the various weather events and cycles of climate variability. Everything from El Nino patterns to marine heat waves that cause the system to fluctuate. Under normal conditions, these waves would rise and fall within a predictable range, their peaks and troughs determined by the energy within the system. But now, imagine we begin to steadily add more water to the pool. The baseline water level rises, and the bottom is no longer where it once was. If we introduce the exact same wave into this fuller pool, with no change to its energy or structure, its crest will now reach a higher absolute point than ever before. This is not because the wave itself grew stronger, but because the entire system it inhabits has been elevated. With the pool now fuller, every single wave, even an identical one, climbs higher. This is precisely the dynamic now playing out in our world's oceans. The baseline temperature, the water level in our planetary pool, has reached an unprecedented high. This means that every fluctuation, every anomaly, and every atmospheric response now begins its journey from a higher starting point. So, when we hear reports of a marine heat wave, a powerful ridge of high pressure, or an unusually warm pocket of air, we are not just witnessing the anomaly in isolation. We are seeing that anomaly amplified by and stacked upon a record-shattering baseline. The implications of this are profound, suggesting our old frameworks for understanding weather may no longer fully capture the new reality. The situation becomes clearer when we examine specific events, such as the Category 5 marine heat wave observed off the coast of Baja California. Its extreme nature is not derived solely from the anomaly itself. It is considered extreme because that anomaly is unfolding on top of the warmest global ocean baseline ever documented. The waters in that region were already warmer than normal before this specific event even began to form. Consequently, when the heat wave did develop, it drove temperatures into a range that may have been physically unattainable in previous decades, even if identical atmospheric conditions had been present. The same principle applies to the record-breaking April heat wave that has spread across the eastern United States. The ridge of high pressure responsible for pushing temperatures into the upper 80s and low 90s is, on its own, a highly unusual event, ranking in the 97th to 99th percentile for this time of year. But this ridge is not forming in a vacuum. It is interacting with an atmosphere that is directly coupled to an ocean system at a record-warm baseline. This connection is critical because the ocean acts as the primary engine for the atmosphere. As the ocean surface warms, it transfers immense amounts of heat and moisture into the air above, essentially providing more fuel for weather systems. Therefore, when this already rare ridge formed, it was drawing from an environment where the background energy level was already elevated. The result is that the atmospheric response, the actual surface temperatures we feel, can climb far beyond what historical analogues might lead us to expect. It is not simply that the ridge is strong. It is that this strong ridge is being fed by a system already running hotter than at any point in our observational history. This combination of an elevated baseline and an extreme anomaly is what gives rise to truly unprecedented conditions. The novelty is not that the individual components have never been seen before, but that they are now compounding in ways that push the entire system past its previously observed limits. This is the difference between a single powerful event and one that shatters records across multiple regions at once. And this compounding effect is not a distant future concern. It is manifesting in real time, directly contributing to the events of April 2026, where the heat is not just early or strong, but amplified by the upward shift of the entire system beneath it. What makes this situation even more consequential is what may be coming next. The Pacific Ocean is not merely warm, it is in a state of active transition. Deep beneath the surface, vast pools of unusually warm water are migrating eastward, a classic precursor signal for the development of an El Nino. Should these subsurface anomalies continue their journey, eventually rising and spreading across the ocean's surface, they would introduce yet another layer of warming on top of the already elevated baseline. This raises a critical question. What happens when a powerful natural cycle unfolds in a world that is already supercharged? To appreciate why this matters, a look at history is illuminating. The El Nino of 1997 to 1998 stands as one of the most potent on record, causing widespread atmospheric disruptions around the globe. Similarly, the 2015 to 2016 El Nino was exceptionally strong, driving extreme weather patterns across many regions. Yet, both of these historic events occurred on top of global ocean baselines that were significantly cooler than what we observe today. Their starting point was fundamentally different. If the current system evolves into an El Nino of comparable or greater strength, it will not be launching from the same conditions. It will be building upon a baseline that is already at a record-breaking level. This does not mean we can simply add a degree of warming here or there to calculate precise outcomes. Climate systems are deeply nonlinear. They do not scale in simple, predictable ways. What it does signify, however, is that the atmosphere will have access to a greater reservoir of energy than it did during those previous major El Nino events. More energy in the system inherently increases the potential for extremes. It narrows the gap between what we once considered severe and what could become truly unprecedented. Events that might have been rare but manageable in the past could cross critical thresholds, entering a territory that lacks a clear historical precedent. And it is here that our uncertainty grows, not from a lack of data, but because the system itself is beginning to enter configurations that have never been fully observed before. This situation brings us to a fundamental truth about our predictive capabilities. Climate and weather models are sophisticated tools constructed from historical data, established physical laws, and complex statistical relationships. While their accuracy has improved dramatically over the decades, they are inherently bound by the range of conditions on which they were trained. This raises a profound question about the very nature of our predictions when the world operates outside of known parameters. When the entire system begins to move beyond historical precedent, as baselines shift and multiple extreme events overlap in novel ways, these models can start to show their limits. We are already witnessing indications of this. The forecast models for this April heat wave, for instance, were continually adjusted upward as new data became available. Yet, even with these revisions, they frequently underestimated the temperatures that were ultimately recorded. This gap between expectation and reality should not be seen as a simple failure of the models. Instead, it is a signal suggesting that the climate system may be reacting to the underlying conditions with greater intensity than we anticipated. And those conditions are far from stable. The Pacific Ocean is still in a state of flux, with immense subsurface heat yet to reach the surface. The official El Niño signal has not even formally emerged. In other words, the entire system is still in a period of transition. The forces driving this unseasonable heat wave are not yet fully formed, which leads to a deep and unsettling uncertainty. If the atmosphere is already generating record-shattering conditions in response to a signal that is only partially developed, what might happen when that signal reaches its full strength? What can we expect when the additional heat from a mature El Niño is layered upon a global ocean already at a record-high baseline temperature? There is no straightforward answer to that question, and that is precisely the point. We may be on the threshold of a new climate regime, one where our historical analogues, our primary guides for understanding future behavior, become increasingly unreliable. This is not because the laws of physics have changed, but because the fundamental boundary conditions of the system have been altered. The Earth system we are observing today is not the same one that generated the extremes of the past. It is a system operating with more energy, higher baselines, and potentially more powerful feedback loops. This doesn't guarantee that every single event will be more severe, but it does raise the probability that when extreme conditions arise, they will have the potential to shatter previous limits. It reinforces the idea that what we are seeing now, the record April heat, the marine heat wave, the premature atmospheric response, is not an isolated event. It is a piece of a much larger pattern, a pattern in which the floor is rising, the waves are building, and the timing of events is shifting. It is a pattern where the system begins to react long before the main event has even arrived. And if this trend holds, the events of April 2026 might not be remembered as a peak, but rather as the moment the system began to reveal its new potential. To truly grasp the situation, we must examine the timeline with precision, as this is where much of the misunderstanding arises. As of mid-April 2026, the equatorial Pacific Ocean has not officially met the criteria required for the declaration of an El Niño event. The key metric, the Oceanic Nino Index, or ONI, remains below the plus 0.5 degrees Celsius benchmark that formally defines El Niño conditions. On paper, according to the official datasets and classification systems, the climate is still in a neutral state. If one were to look solely at that number, the conclusion would be that the system has not yet transitioned. But that conclusion would be dangerously incomplete because the data tells only part of the story. Beneath the surface of the ocean, quite literally, the system is already in full motion. Vast quantities of exceptionally warm water, in some areas reaching nearly 5 degrees Celsius above the average, are migrating eastward across the equatorial Pacific. It is important to understand that these are not yet surface anomalies. They are immense reservoirs of subsurface heat transported by downwelling Kelvin waves. These waves, acting like massive underwater conveyor belts, were set in motion by bursts of westerly wind over the past several weeks. Their function is to carry heat from the western and central Pacific toward the eastern basin, where it will eventually rise and begin to interact directly with the atmosphere. This entire process is still underway. The heat has not fully surfaced, and the critical coupling between the ocean and the atmosphere, the phase where warmer sea surface temperatures begin to reshape global weather patterns, is not yet complete. What we are witnessing is the loading phase, the build-up, the preconditioning of a much larger event. And yet, despite the system having not fully transitioned, despite the official signal remaining undeclared, the atmosphere is already responding with incredible force. The Category 5 marine heatwave off the coast of Baja California is not the culmination of this process. It is its leading edge. It is the place where this deep, hidden heat is beginning to break through to the surface. Simultaneously, across the continental United States, the atmosphere is locked into a pattern that is, by any statistical measure, extreme for this time of year. A 99th percentile ridge of high pressure is driving temperatures into the 80s and 90s from Washington, D.C. to Boston in the middle of April, while also contributing to a cascade of other weather extremes nationwide. The crucial insight here is the timing. What we are observing is not the response to the mature state of the system. It is the atmosphere's reaction to a precursor state to the loading, not the discharge. Once you understand that distinction, a very serious question naturally follows. If the precursor alone, this incomplete and still evolving setup, is capable of generating a 99th percentile atmospheric pattern that outperforms model forecasts and breaks records across major cities, then what will the fully developed system produce? What happens when the heat that is currently hidden deep in the ocean finally surfaces? What happens when the powerful feedback loops that define a mature El Niño lock into place? The honest answer is that we do not know with precision. This uncertainty is not a weakness in the science. It is a direct reflection of the immense complexity of the system we are dealing with. Climate and weather are non-linear systems, which means their responses are not always proportional to the inputs. Small differences in the initial conditions can ultimately lead to vastly different outcomes. When you compound this with the fact that the entire global system is operating on top of a record-high ocean temperature baseline, you are dealing with a configuration that has no perfect historical precedent. We are navigating without a map from the past, because the landscape itself has changed. What scientists can do is define a range of plausible outcomes, preparing us for a future that may look very different from anything we have seen before. At the lower end of the predicted range, the climate system develops into a moderate or even a strong El Niño. While disruptive, the atmospheric response remains within the boundaries of what has been observed before. Summers tend to be hotter than average, severe weather can become more active, and rainfall patterns shift in ways that are largely familiar. It is a significant disturbance, but not one that fundamentally rewrites our expectations of how the climate behaves. Yet, there is also an upper end of this range of possibilities. In such a scenario, the immense reservoir of subsurface heat fully emerges at the ocean's surface. The coupling between the sea and the air above it strengthens with astonishing speed, triggering a feedback loop that drives vast changes in circulation. This could push Cinquenta jet stream into configurations that bear little resemblance to anything in the modern observational record. In a future like that, we would face not just isolated extremes, but persistent, large-scale shifts in weather patterns. This could mean extended periods of intense heat in regions unaccustomed to it, prolonged disruptions to the rainfall that agriculture relies upon, and atmospheric blocking patterns that lock these devastating conditions in place for weeks or even months at a time. Between these two potential outcomes lies a wide spectrum of possibilities, a probability distribution that scientists are working tirelessly to narrow. One of the most vital clues to where we might land on that spectrum comes from the behavior of the forecast models themselves. At present, the various forecasting methods, from statistical models and dynamical climate models to hybrid systems, are generating a relatively broad spread of outcomes for the months ahead. This spread, however, is not random noise. It is a signal in its own right. When different models converge on a single forecast, it generally indicates that the system is well understood and its potential responses are limited. But when the models diverge, producing a wide array of possibilities, it typically means the system is in a highly sensitive state. It is a state where even small changes in how conditions evolve can lead to profoundly different results. This is the delicate moment we find ourselves in now. a time defined by this wide divergence in what the future might hold. There is another layer to consider, and it is the direction of recent surprises. Over the last several weeks, the atmosphere's response to the warming ocean has not simply met expectations, it has consistently exceeded them. As forecasters have adjusted their predictions upward, reality has still proven to be hotter, stronger, and more amplified than anticipated. This recurring pattern of underestimation suggests a critical possibility. The risk may not be distributed evenly across the range of potential outcomes. Instead, it seems to be skewed toward the more powerful and extreme end of the spectrum. To understand why this might be the case, we must look deeper into how an El Niño actually functions not just as a temperature anomaly, but as a deeply interconnected system. The defining characteristic of a fully developed El Niño is not merely the presence of warm water in the Pacific. It is the powerful feedback loop that ignites between the ocean and the atmosphere once that warmth becomes persistent and widespread at the surface. Under normal conditions, the tropical Pacific is governed by the Walker circulation, an immense atmospheric conveyor belt that flows from east to west. Warm water naturally pools near Indonesia in the western Pacific, fueling convection and causing air to rise. This air then travels eastward at high altitudes, cools and sinks over the eastern Pacific, and flows back to the west as the trade winds. These very winds help to push the warm surface water back toward the west, reinforcing the entire cycle. An El Niño event fundamentally disrupts this delicate balance. As warm water begins to spread eastward across the Pacific, the temperature difference from one side to the other weakens. This causes the center of convection to shift eastward, which in turn weakens the trade winds. As those winds falter, they allow even more warm water to surge east and rise to the surface. This process creates a positive feedback loop. More warm water leads to weaker winds, which then allows for even more warm water, further weakening the winds in a self-reinforcing cycle. The ultimate strength and speed of this feedback mechanism are what determine just how powerful an El Niño will become. And right now, the conditions in the Pacific are unusually favorable for that loop to activate with exceptional force. The subsurface reservoir of heat is already immense. Enormous underwater currents, known as Kelvin waves, are already transporting that heat toward the east. And all of this is occurring within a background ocean that is already warmer than at any other point in the observational record. It is as though all the necessary ingredients are in place, waiting for the process to begin. These factors significantly increase the likelihood that once this coupling process truly begins, it could proceed with remarkable speed and intensity. This is precisely why this moment holds so much significance. We are not just observing a system in motion, we are observing a system as it approaches a potential inflection point. This is a threshold beyond which the fundamental dynamics of the system could change qualitatively, not just quantitatively. Before such a threshold is crossed, the system responds in a predictable, linear fashion. After it is crossed, the entire system can reorganize itself in ways that are difficult to foresee. In this context, the record-breaking April heatwave was not the main event. Instead, it should be seen as a signal, a clear indication that the system is already sensitive enough to generate extreme responses well ahead of schedule. It is evidence that the atmosphere is already feeling the influence of a Pacific Ocean that has not yet fully unleashed its energy at the surface. This leads to a final, and perhaps uncomfortable, realization. If the atmosphere is already capable of producing unprecedented weather patterns in response to a merely partial signal from the ocean, then the full expression of that signal, when it finally arrives, may not simply scale up what we are seeing now. It could potentially push the entire climate system into behaviors that we do not yet fully understand. This is not about predicting one specific outcome with certainty. It is about recognizing the unique structure of the moment we are in. The system is loaded with energy. The coupling process between ocean and atmosphere is underway but still incomplete, and while the atmospheric response has already begun, the range of possible futures remains unnervingly wide. In other words, we are watching a system approach a point where its very nature could change. And the most important thing to understand is that the April heatwave was not the story itself. It was the announcement that the story is about to begin. The term Super El Niño is frequently used in headlines and online discussions, but within the scientific community, it holds a very specific meaning. Understanding this distinction is critical to grasping what is truly at stake. This is not simply a dramatic label for a particularly strong event. It refers to a narrow category of El Niños that sit at the most extreme upper edge of what our climate system has produced in the entire modern observational record. To understand where that threshold lies, one must look at how these events are formally classified. The benchmark for this measurement is a specific area known as the Nino 3.4 region, located in the central equatorial Pacific. It is there that scientists meticulously track the sea surface temperature anomaly, the deviation from the long-term average, which the intensity of an El Niño event is measured by how much warmer the equatorial Pacific waters become compared to their long-term average. A moderate event is typically characterized by a peak temperature anomaly of about 1 to 1.5 degrees Celsius. When this anomaly climbs to between 1.5 and 2 degrees, the event is classified as strong. Yet, there exists another category, one not formally codified but widely recognized by scientists for events that surpass the 2-degree Celsius mark. These are what we call super El Niños, and they are exceptionally rare. In our modern instrumental record, which benefits from decades of high-quality satellite and buoy data, only 2 events have definitively and sustainedly crossed this threshold: the 1997 to 1998 event and the one that followed in 2015 to 2016. These are far more than just statistical curiosities. They are planetary-scale phenomena that can fundamentally reorganize the Earth's atmosphere. The 1997 to 1998 event saw the crucial Nino 3.4 region peak at an anomaly of roughly 2.4 degrees Celsius, while the 2015 to 2016 event was even more intense, reaching around 2.6 degrees. On paper, these numbers may not seem profoundly different from a 1.8-degree anomaly. However, within the complex, non-linear dynamics of our coupled ocean-atmosphere system, that small difference has enormous consequences. The impacts of these super events were not merely stronger versions of a moderate El Niño. They were qualitatively different. This means the atmospheric circulation patterns they generated, the configuration of jet streams, the paths of storms, and the global distribution of rain and drought did not simply amplify existing trends. Instead, they shifted them entirely. The teleconnections, which describe how climate changes in one region influence distant parts of the world, grew stronger, more persistent, and far more widespread. Entire continents experienced sustained anomalies that persisted for months, altering the very character of seasons. This is the category of event we are contemplating when we discuss the potential for a super El Niño in the current cycle. It is crucial to be clear. This is not a confirmed forecast, nor is it even the most probable outcome according to current data, but it is also no longer a remote, fringe scenario. The latest probability assessments from institutions like the Climate Prediction Center have shown a trend that warrants our close attention. With each successive update, the likelihood of El Niño's development in the coming months has increased, reflecting the very signals we have been examining. The rapid warming of the ocean surface, the presence of significant subsurface heat anomalies, and the steady eastward march of that heat through Kelvin waves. Even more telling is what we see when we look inside the ensemble forecasts. These are collections of multiple computer model simulations that explore the many different ways the climate system could evolve. Within these ensembles, a subset of model runs has begun to appear that was not as prominent just a few months ago. These specific simulations are projecting peak Nino 3.4 anomalies that exceed the 2 degrees Celsius threshold for a super El Nino. While not all models agree, and many still predict a weaker event, the very presence of these high-end outcomes is significant. In forecasting, the distribution of possibilities can be as important as the average prediction. If all models cluster around a moderate outcome, confidence is high. But when the spread of possibilities widens, and especially when its upper edge extends into extreme territory, it signals that the system holds the potential for something far more intense than the average projection suggests. Just a few months ago, a super El Nino scenario for this year would have been considered a low probability outlier. Today, it resides within the envelope of plausible outcomes that scientists are actively evaluating. It is this shift in status, from improbable to plausible, that makes this moment so critical. It does not guarantee that a super El Nino will happen, but it does confirm that the necessary conditions are present enough that the possibility can no longer be dismissed. If we take that possibility seriously, the immediate question becomes what it would mean for regions like North America. The impacts of a super El Nino are never evenly distributed. They manifest differently based on geography, season, and interaction with other atmospheric patterns. Looking back at the 1997 to 1998 event offers one of our clearest points of reference. During that winter, the jet stream across the United States shifted dramatically southward. This profoundly altered storm tracks, funneling an unusually active parade of storms into California and the southern tier of the country. The result was a devastating combination of heavy rainfall, flooding, and mudslides, as region after region was hit by relentless storm systems. At the very same time, the northern tier of the United States experienced a completely different reality. With the storm track displaced so far south, these regions were left significantly warmer and drier than average. This reveals a key characteristic of strong El Nino events. They do not simply increase precipitation everywhere, but rather redistribute it on a continental scale, creating simultaneous extremes of flood and drought. Temperature patterns are also affected in ways that echo what we are already beginning to observe. Strong El Nino events are consistently associated with above-average winter and early spring temperatures across much of the central and eastern United States. This means that the kind of premature warmth that can make April feel like early summer can become a sustained pattern rather than a brief anomaly. Instead of just a few days of record heat, entire seasons can trend warmer than normal, altering ecosystems and human activity alike. Finally, we must consider the question of tropical cyclones, which adds another layer of complexity. One of the most frequently cited effects of El Nino is its tendency to suppress hurricane activity in the Atlantic basin. This occurs because El Nino increases vertical wind shear over the tropical Atlantic, which disrupts the vertical structure of storms and inhibits their development. It is often presented as a simple trade-off. A warmer Pacific means fewer Atlantic hurricanes. But this framing is incomplete. The suppressive effect in the Atlantic is not guaranteed and depends on the specific structure of the El Nino. Simultaneously, while conditions in the Atlantic may become hostile for hurricanes, the opposite is happening in the eastern and central Pacific. The very same El Nino that increases wind shear in the Atlantic is creating highly favorable conditions for cyclone development elsewhere. Warmer ocean waters, lower wind shear, and increased atmospheric instability combine to create a perfect environment for storms to form and intensify. This demonstrates that El Nino does not simply calm the world's oceans, it rearranges the zones of activity, shifting the risk of powerful cyclones from one basin to another. In the presence of a super El Nino, This global redistribution of weather patterns can grow even more distinct. While the Atlantic may experience a downturn in storm activity, that energy doesn't just disappear. Instead, it can shift, potentially fueling a significantly more active storm season across the Pacific. This suggests the total number of storms worldwide may not substantially decline. Rather, their locations and intensities are altered, creating profoundly different risks for different regions. It is within this context that recent events begin to feel less like isolated occurrences and more like preliminary signals of a larger shift. The rapid intensification of Super Typhoon Slaku into a Category 5 storm in April, long before the season's traditional peak, is a compelling example. This powerful storm formed over ocean waters that were already unseasonably warm. Such early and intense storm formation is not characteristic of a neutral climate system. It implies that the ocean has already reached a state capable of supporting extreme weather, raising the question of what might happen if these conditions persist. Should this evolve into a fully coupled El Nino, the Pacific basins could see this pattern continue, with storms forming earlier, strengthening faster, and potentially achieving greater peak intensities. While this outcome is not guaranteed, it remains entirely consistent with the physical conditions we are currently observing. When we assemble all these individual pieces, a more cohesive and concerning picture begins to emerge. The potential for a super El Nino is not merely about a single metric crossing a designated threshold. It is about the convergence of multiple factors that would enable that threshold to be met and the cascading response from the entire climate system that would ensue. What we are witnessing is a Pacific Ocean that is already warm at the surface, holds significant heat far below the surface, and is situated within a global ocean that has just registered its highest temperatures on record. This specific combination of conditions is something we have not seen before in precisely this form. The powerful events of 1997 to 1998 and 2015 to 2016 offer our closest historical parallels, but both of those episodes developed from a foundation of lower baseline temperatures. The current system, should it mature into a super El Nino, would be launching from a starting point that is already substantially elevated. This leads to an honest summary that is not one of certainty, but one of risk assessment. A super El Nino scenario is plausible, appearing within the spread of current ensemble forecasts. It is being carefully analyzed by scientists because the underlying conditions clearly support its potential. If such an event does materialize, it would represent a level of force on the global atmosphere that, based on historical analogues, could produce some of the most significant weather and climate impacts of the modern era. This does not mean it is destined to happen. It does mean, however, that to ignore the possibility would be a mistake. The data does not support dismissal. It commands our attention. There is a particular scenario that sits at the confluence of everything we have been exploring, yet it is almost never featured in mainstream discussions of climate risk. This is not because the scenario is physically impossible or lacks a scientific basis. It is because it occupies an uncomfortable space where the probability is low, but the consequences are extraordinarily high, and historical precedent is scarce. It is exactly this type of outlier event that gains relevance when the underlying system changes, when baselines rise, and when the very definition of what is normal begins to blur. Right now, along the coasts of California and Baja California, sea surface temperatures are so high they are classified as a Category 5 marine heatwave. This is the most extreme category on the scale, signifying conditions that are far outside the bounds of typical variability. We have already touched upon the ecological ramifications of such an event, the immense stress on marine ecosystems, the disruption to fisheries, and the cascading effects that ripple through the entire food web. But there is another implication that receives far less focus: one that is rooted in the physics of tropical cyclones. Tropical cyclones, known as hurricanes or typhoons depending on their location, are fundamentally heat engines. They draw their immense power from warm ocean water. For a storm to form and sustain itself, it requires a sufficiently warm surface layer, typically around 26 to 28 degrees Celsius. Crucially, that warmth must also extend deep enough into the water column to prevent the storm's own violent churning from bringing cold water to the surface, which would cut off its own fuel supply. When these conditions are not met, storms inevitably weaken, but when they are exceeded, storms can intensify, sometimes with astonishing speed. Historically, the waters off the coasts of Baja California and Southern California have been too cool to support sustained tropical cyclone activity, especially outside the late summer and early autumn months. Storms that form farther south, in the eastern Pacific, have almost always weakened as they track northward, encountering these cooler waters that effectively extinguish their convective engines. For decades, this has served as a reliable climatic boundary. But that boundary is not a permanent fixture. It is defined by temperature, and as we are seeing in real time, that temperature is changing. As of a recent April, months ahead of when such conditions would normally be expected, portions of the northeastern Pacific along Baja California are already approaching or even exceeding the temperature thresholds required to sustain a tropical cyclone. This does not mean the entire coastline is uniformly at this level, nor does it mean all the other atmospheric ingredients for storm formation are in place. What it does mean, however, is that one of the most critical limiting factors, the availability of sufficiently warm water, is no longer the reliable constraint it once was. As that constraint loosens, a new and unsettling category of possibility begins to open. To truly grasp what this might look like, it is helpful to examine one of the few historical examples that comes close. In September of 1997, during the peak of one of the most powerful El Nino events on record, Hurricane Nora formed in the eastern Pacific and followed a highly unusual trajectory. Instead of rapidly weakening as it moved north, Nora maintained significant intensity all along the Baja California coast. The storm eventually made landfall in Mexico and continued its northward journey, delivering substantial rainfall to parts of the southwestern United States, including Arizona and Southern California. Nora was not just another hurricane, it was an outlier, a preview of what is possible. Its remarkable track and persistence were enabled by ocean temperatures that were exceptionally warm for that region, even for the peak of the season, reminding us that what was once an anomaly could become a future possibility. The Super El Nino of 1997 to 1998 brought elevated sea surface temperatures to the Baja coast, creating conditions that allowed a storm to sustain itself farther north than would normally be possible. Even then, it was considered a truly rare event. Now, let us turn to the present moment. In April of 2026, the waters off Baja California are, in some locations, already approaching the very temperatures that supported that storm's unusual behavior in September of 1997. This is a shift in timing that is difficult to ignore, suggesting the seasonal window for such conditions may be expanding by months. This does not mean a similar event is imminent, or even that one is likely. The formation and evolution of a tropical cyclone depend on a delicate combination of factors, not just the warmth of the ocean. The storm's structure must be protected by low vertical wind shear, so it is not torn apart by differing wind speeds at different altitudes. A pre-existing disturbance, like a tropical wave, is needed to initiate the process, and there must be enough atmospheric moisture to fuel its powerful convection. The point of this scenario, then, is not to claim that such an event will happen. It is to recognize that the range of what is physically possible appears to be expanding. When ocean temperatures reach thresholds that were previously rare or confined to a narrow seasonal window, they begin to remove the natural barriers that once limited certain types of events. And when those barriers are removed, even temporarily, the system can discover new pathways. This is what risk looks like in an environment with a changing baseline. It is not just a matter of familiar events growing more intense. It is about the system enabling event types, timings, or combinations that were previously constrained. A storm tracking unusually far north along the Baja coast and impacting the southwestern United States is not an entirely new phenomenon. However, the conditions that allowed it to happen in 1997 were tied to a very specific set of circumstances at a very specific time of year. What we are seeing now is a shift in those underlying conditions. This change moves this kind of event out of the category of a rare seasonal anomaly and into the broader category of low probability, high impact scenarios that can exist over a longer portion of the year. These are precisely the scenarios that tend to be underweighted in both public discussion and planning, not because they are unimportant, but because they are difficult to quantify and lack a dense historical record. There is also a tendency to analyze these risks in isolation. We discuss heat waves as one category, marine heat waves as another, and tropical cyclones as a third. But in reality, these are all expressions of the same underlying system. The same ocean heat that is elevating temperatures along the Baja coast is part of a broader Pacific thermal anomaly that is also influencing atmospheric patterns over North America. When you connect those dots, the picture changes entirely. The record April heat wave along the eastern United States, driven by a highly amplified ridge, is not an isolated atmospheric quirk. It is linked to the same large-scale redistribution of heat in the Pacific that is raising sea surface temperatures thousands of miles away along the California coast. The subsurface warming, the eastward propagation of heat, and the basin-wide coherence of the anomaly are not separate stories. They are different manifestations of the same process. And when that process reaches certain thresholds, it does not just produce one type of extreme event, it expands the envelope of what the system can produce across multiple categories. That is why focusing on any single outcome, the heat wave, the marine anomaly, or the potential for storms, can be misleading. The real signal is in the combination of these events. The Pacific right now is not just warm, it is structured in a way that allows heat to influence both the ocean surface and the atmosphere in coordinated ways. The Category 5 marine heat wave off Baja is a surface expression. The subsurface anomalies are a deeper reservoir. The atmospheric response over the United States is another layer. When viewed through that interconnected lens, the Baja scenario is not an outlier. It is an example, an illustration of how the current configuration creates possibilities that would have been much harder to achieve under previous baseline conditions. It shows how the same underlying driver can manifest in very different ways depending on location, timing, and the interaction with other factors. This reinforces a broader point that runs through everything we have discussed. The significance of the current moment is not confined to any single metric or event. It lies in the way multiple signals are aligning, from elevated global ocean temperatures and significant subsurface heat in the Pacific to early atmospheric responses and localized extremes that are already pushing into unusual territory. In this context, the Baja coast becomes a kind of preview window, a place where the ocean state is revealing capabilities that the system possesses right now, even if they are not yet fully realized in the atmosphere. It is a reminder that the system does not need to produce the most extreme outcome for that outcome to be relevant. The mere fact that the conditions supporting it exist changes the risk landscape, and that brings us back to the central thread. The same Pacific heat contributing to record-breaking warmth in April across the eastern United States is also raising coastal water temperatures to levels that can support entirely different kinds of extremes. They are different expressions from the same source, Once you see that connection clearly, it becomes harder to think of any single event in isolation. What we are really watching is not a heat wave or a marine anomaly or a hypothetical storm track. We are watching a system whose boundaries are shifting, and with them, the range of what is possible. Let us come back to the beginning. Let us come back to Washington, D.C. in mid-April, sweating through temperatures that belong in July. Let us come back to Boston, where the air mass overhead had the thermal signature of a summer that arrived months early. Let us come back to the National Weather Service offices that adjusted their forecasts upward and still watched as reality blew past them. We must return to the fundamental question that initiated this entire inquiry. Why are these events unfolding now? The scientific framework we have constructed offers a partial explanation. Deep beneath the surface of the Pacific, water that is 5 degrees C warmer than average is propagating eastward, carried by downwelling Kelvin waves. This process is loading the upper ocean's thermal structure from below, causing sea surface temperatures to surge in response. Off the coast of Baja California, a marine heat wave has reached Category 5 intensity, while the waters along the California coast have set new record highs for April. The ONI, which serves as a lagging indicator for a system in rapid flux, is already moving toward the El Nino threshold. For months, the atmosphere has been reacting to these leading signals of transition. A record global ocean temperature, the highest for any month in instrumental history, is raising the baseline upon which all these anomalies are now operating. The atmosphere's reaction to this combined forcing is an amplified Rossby wave pattern, which is generating simultaneous extremes across 5 distinct weather categories. At the heart of this is a heat dome over the eastern United States, so intense that it ranks in the 99th percentile of the entire historical record for April. This is the mechanism we can observe, but it may not be the complete picture. This framework, however, does not fully resolve the central mystery. The atmosphere appears to be reacting with a strength that the known forcing alone cannot account for. The models, which contain our best physical understanding of how atmospheric circulation responds to Pacific Ocean temperatures, have consistently underestimated the magnitude of the current pattern. Even the seasoned forecasters who adjusted these models toward greater warmth found their predictions outpaced by reality. This discrepancy between what was predicted and what has been observed is not random. It is a systematic gap, always leaning in the direction of a stronger than expected atmospheric response. And within that systematic gap lies the unresolved puzzle at the core of this story. What fundamental element of this interaction are we failing to grasp? One possibility is that our models are not yet capturing the true scale of the forcing from the Pacific. It may be that the subsurface anomalies, the elevated global baseline, and the compound effects of multiple overlapping signals are creating a force genuinely stronger than the model's assumptions about the Pacific's current state. This is a plausible explanation, but it carries a troubling implication. As the subsurface heat continues to rise and the El Nino forcing intensifies, our models may progressively underestimate the atmosphere's reaction until they finally catch up to the ocean's actual thermal state. This is an uncomfortable prospect, as it suggests we may be systematically underpredicting the severity of what is to come. An alternative possibility, for which the science has yet to provide definitive evidence either way, is that the atmosphere itself has grown more sensitive to the ocean's influence. Decades of gradual warming may have shifted the background state of the global circulation, amplifying its response to a given forcing beyond what historical relationships would lead us to expect. If the jet stream has indeed systematically weakened, or if Arctic amplification has altered the temperature contrasts that govern wave behavior, the system could be fundamentally changed. If the high ocean baseline has redistributed tropical convection in a way that magnifies downstream teleconnections, then the same El Nino forcing that produced certain atmospheric patterns in 1997 and 2015 might trigger much larger responses today. This would mean that the historical analogues we depend on to forecast El Niño's impacts are now systematically conservative, understating what our current climate system is capable of producing. We do not yet know which of these possibilities is correct, and it may be some time before we do. What we can say with certainty is that the system is already operating far outside the bounds of normal prediction, even as it has yet to reach its peak forcing. The April heatwave is merely a preview. The Pacific has not finished loading its heat into the upper ocean. The great subsurface anomaly has not fully surfaced, and El Niño has not yet been officially declared. And crucially, the Walker circulation feedback loop, which drives the most extreme impacts of an El Niño, has not yet fully activated. Despite all this, the atmosphere is already exhibiting behavior at the 99th percentile of its entire April historical range. There is a familiar narrative that often accompanies extreme weather events. It is a story that says, "This was unusual, but we understand why it happened. Here is the science that explains it, and this is how we can predict the next one." That narrative is comforting because it implies comprehension and control. We saw the event, we explained it, and we can anticipate the future. For the current situation, that narrative is only partially true. We understand the broad strokes of why April 2026 is behaving as it is, but a residual remains a gap between prediction and reality, between the expected forcing and the actual atmospheric response that this narrative cannot fully explain. It is this residual that should command our attention, for it suggests the atmosphere is telling us something we have not yet fully learned how to hear. As the eastern United States bakes in April heat that feels like summer, a vast reserve of water, 5 degrees Celsius above average, continues its eastward journey deep beneath the Pacific, still approaching the surface, still waiting to fully arrive. A Category 5 marine heat wave is now established along the Baja coast. A super typhoon formed in April, fueled by ocean heat content typical of the peak season. Just 1 month ago, the global ocean set an all-time temperature record for any month in history. And yet, El Niño has not officially started. The Walker circulation feedback has not engaged. The discharge of subsurface heat has not completed. Every tool we possess for prediction underestimated this moment. And this is not the moment itself. This is only the approach. The record April heat, the flooding rivers in Michigan, the fire weather in Texas, the out-of-season typhoon in the western Pacific, and the Category 5 marine temperatures off California are not separate events that just happened to cluster in April 2026. They are dispatches from a planetary system in a state of profound transition, one whose final destination we cannot yet clearly see. They represent the kind of signals that, in hindsight, will look like they were screaming the answer at anyone who was paying attention. They are the kind of warnings that get quoted in retrospective analyses, written long after the main event arrives, when people ask, was there any warning? There was. There is. In the middle of April 2026, an extraordinary heat wave descends upon the eastern United States. The intensity of this heat is something no model had foreseen and no historical record had ever suggested for this time of year. This event is a clear indication that the global climate system has not yet settled, but is actively building towards an unknown conclusion. The great engine of this change, the Pacific Ocean, has not yet finished delivering its message. And the atmosphere itself, the very system that defied every forecast, has already begun its powerful response. It has generated 5 simultaneous categories of extreme weather from a forcing that is not yet fully present. It is as if the atmosphere is reacting to a preliminary signal, as if it were the main event, and it has not even received the complete transmission. The ocean is still speaking, its message unfolding in real time. This leaves us with a critical question. Are we listening with enough care to understand what it is trying to tell us, before we are forced to learn the answer the hard way?